have already heard about this topic, Maldrone, on the news? Oh, okay. That's a good. So the actual name of the presentation was not Maldrone. It was hacking drones. I made a blog post about this. A portion of it was Maldrone, and I made a blog post about it like a week back, like a pre-conference demo sort of thing, which got a lot of media attention. It got almost 500,000 views on the blog, and in 4 days I got 50,000 views on my YouTube. And then there are so many people who didn't read the blog started asking questions, which is related to what news articles have written. Another thing what happened is in US, one guy flew, so this is called DJI Phantom drone. Some guy flew this drone into White House. So my blog and then that incident, press started making stories and they created a lot of fuss about it. So that's how it got a little bit of media attention. So a lot of questions people ask me, I would be responding to those questions in my talk, and that's why I title the talk as Maldrone itself. So why a talk on drones? There are almost 70 different countries building drones, autonomous
self-contained helicopters
machines that can
which
take
are ready to
autonomous
fly
decisions.
out of the box.
Many lethal decisions in the future will soon be taken care by drones. What you see over here is a military drone, a small one which is used by the UK military. It's too small, it can fly almost 1 kilometer away, take surveillance videos and comes back with feeds. You can't even spot while it's flying. So this is already there, and videos like this are already on the on the internet and the YouTube, and this is what kind of motivated me. And there are so many other researches happening in this field. People are making drones which can fly like birds and capture things. And then there was this guy, FPS Russia, who created who actually planted a small SMG on a drone and started shooting things up. I'm not quite sure about the authenticity of this video, but I like the laugh on this guy's face. So videos like this kind of, was kind of cool. I thought, this would be the new technology of the future. Not just videos. I really wanted to learn artificial intelligence and, drone-related technology. One of the main reasons was this TED video, which you see on the right, by Raffaello D'Andrea. He demonstrated how drones could communicate together and how they can do tasks which humans cannot by default. And then there is this concept of Nixie. We know how fascinated we are with selfies, right? I mean, we are so obsessed with selfies. Now, Intel has invested in a technology that can actually act as a wrist watch. It can fly off from your hands, take a selfie of yours, and come back. So there's a prototype for this already, and they are actually building this thing. And then you might have already heard about Amazon, who's trying to deliver drones, who's trying to deliver packages via drones. And they're trying to get this technology running in the next 5 years. All these things were quite motivating, and I thought, why not be prepared for machine revolution? And then there are a lot of practical attacks on drones, which is already out there. One of the interesting ones was the Iran hijacked US Sentinel. What they actually did is they jammed the drone's GPS signals. Once it moves out of, once it didn't have a GPS signal, they sent fake GPS coordinate, made it land in their own territory. They reverse engineered the drone and extracted all the all the video recordings of the surveillance. They might have not properly encrypted the video footage. So these things have already happened. And then there is this guy from the University of Texas who even did the same GPS spoofing attack. They did a demo with a small drone which they had. So all these incidents put together, I had like n number of questions. One of them was, we buy drones from so many countries. People buy drones from their neighbors. What if the drone which we brought is backdoored? Or is it possible, or what would it take to backdoor a drone? Also, what if we find and identify a security issue in a drone, what would be the impact on it, and how is it that we could find them. So I started learning, and I'm still learning. So what I'm going to present right now over here would be part of what I've learned so far in the journey of answering these questions. Myself, Rahul Sasi. I work as a security engineer for Citrix. I speak at conferences. I have all my GitHub, Twitter, LinkedIn, everything has got the handle FB on HTS. Also, I'm the member of the community called Garage for Hackers. One of the frequently asked questions related to this research is, what is Citrix involvement in this? Whatever we are demonstrating is for educational purpose only. Working at Citrix has given me the flexibility to conduct research in any area I'm passionate about. This Maldrone research was specifically done by me in my free time and does not reflect the products or vision of Citrix. That means Citrix doesn't give a damn about what I do in my free time. And that is the reason why they are one of the top companies to work for. We have a booth over there, and we have the security manager as well over here. Do talk to him. So about Garage for Hackers, it's a community of like-minded people. We have members all across the world, security, consulting, everything. We have people over here as well. Do talk to them. It's a forum-based community which could be reached at garageforhackers.com. As part of the initiative, we do something called as webcast every month. We have done almost 6 webcasts. We bring talented people who are expertise in a particular subject, bring and make them talk to you on a particular topic. We had viewers from almost 20 different countries. We had people from Russia, US, Germany, Argentina, talking on n number of subjects ranging from client-side security, browser crash analysis, reverse engineering, ARM exploitation, or name what you want, and we were bringing those people. And all these people do spend their free time to contribute back to the community, and that's why we have that. Oh, even Mario, who is already here, he gave a webcast as well. We conduct CTFs as well every month, not every month, like couple of them. We get more than 30,000 views on our page every month. We responsibly report bugs to a lot of browser vendors and other people. Our members participate in bug bounty programs, and we actually share the bug reports over there. And members in our community talk in various conferences all across the world. And we contribute. We have a lot of open source projects in-house which we build. We mentor students, get them introduced to information security. And one of our guys has a startup right now called Secure7. One of the big things we did last year was we raised almost 1 lakh rupees for Kashmir Relief Fund. Not just us, hackers all around India gathered this money, and we brought relief aid. And one of our members, Rashid Bhatt, actually went to Kashmir and helped the people over there. Join our mission. You could follow us on Twitter, Facebook, or wherever you guys are. So the topics covered would be the following. We'll have a bit of drone aviation principles, a bit of DDoS attacks on drones, ARM reverse engineering, security vulnerabilities and how to find them in drones, and then a concept of malware for drones, which we call Maldrone. So there are almost multiple types of quadcopters. We are specifically going to deal with something called as quadcopters, the one you see over there. I mean, actually copters, and in that multicopters, quadcopters. Multicopter, the name comes from, the variety is based on the number of motors they use. You can see a bicopter which has got 2 motors, and then you can see something called as octocopters which got 8 motors. For our demos, we use something called as a quadcopter which has got 4 motors. Drones are very expensive. High-end drones are not easily available. There are few personal drones available. We use them. We use something called as a Parrot AR drone. That is here, this black guy, and this white guy, DJI Phantom. They cost around 1,500 USD. That is about 1 lakh, nearly 1 lakh rupees. if you purchase from outside India, but inside it's a little more expensive. I will explain why we choose this, because they are very similar to the actual technology which is being used in any other professional drones. The technology is same, and that is why the price is high. The drone communicates on two different channels. One is called the line of sight communication, and then the satellite. So when so the line of sight happens on for C-band, for military range 500 to 1000 megahertz, and for civil drones it's 2.54 gigahertz. So this guy runs on a 2.5 gigahertz, and then if it moves out of the line of sight, that moves out of the radio frequency, it automatically connects to the satellites and understands its position. So this one uses a GPS. So if it loses this radio frequency signal, it can have a range of 1 kilometer. If it goes above, it will actually connect to the GPS, gets its coordinate. It will also know which coordinate it started from and actually comes back. I won't be using this thing for demo right now because this thing works on GPS by default. The stabilization is based on GPS, and I'm not getting GPS signals inside. So for all the demos we'll be doing on that, this input comes from the sensors which it has. So the flow of the talk would be mostly concentrated on that one. And I was not getting GPS anywhere around this particular thing, the proper GPS. So, so this is what happens. When the drones take off, there would be a commanding center, the base station or whatever you call it, which sends radio signals, communicates to the drone. Once it loses out of line of sight, it connects to the satellites, now try to understand what is happening with the drones. It tries to find the location, and that's how both of them works. But the interesting thing is, if something loses out of signal, I mean, let's say if someone jammed the GPS as well, what would the drones by default do? So all the drones have, or at least the military drones have a functionality that it would understand, or there is a portion of control algorithms that tells him to take actions of its own. So that means there is no more control happening by human interventions. The drones can perform of its own once it loses out of control. So this is the technology which we are trying to hack into. The decision-making units where drones can actually take over and perform actions. Before moving into before moving into hello before moving into, is it working? Okay, no, I don't think it's working. Okay, it's now working. All right. So before moving into the software part, we'll explain how the mechanical movements of these quadcopters are. So what happens is this is got four propellers. Each of them are symmetric to each other. Each arm is 90 degrees apart. So what happens is opposite propellers mounted create opposite force. So these two propellers will be creating opposite force, and again these two would be creating opposite force. That makes them stay up, and so it's a constant thrust which is going down, and that makes them float in the air. And then they have four different movements. One is called roll. That means the drone would actually go forward, and then something called as a pitch and yaw. Yaw is something means it rotates on its own axis. We'll have a small demo on how that works. So this is you. Can you see the screen? Okay. So this is the roll. This is roll. This is pitch. And yo is turning back and come back. Right, cool. So, let's be here. So those are the moments actually, which we just demonstrated. The roll, pitch, and yo, which actually rotates on its own axis. So that's how it basically works. Now, how do it mechanically function? So when it has to move forward, what happens is these two motors rotate faster than the ones in the front. That creates a small displacement in the angle, which makes them push forward. And the same happens, it'll tilt back. It pushes backwards, and the rotation or the way it moves is basically on how the rotors function. So that's exactly how this works. So, but if you have noticed something, even when I was not controlling it, it was stabilized. It stood here for some time. I mean, physics, when you put thrust on something, it has to constantly keep moving, right? Something cannot stay in a place if force is, there's force. It has to keep moving. So how does these copters stay stabilized in one place? So for this mechanical function to work, there needs to be a motion detection, direction sensing, and orientation sensing, and all this, they have special sensors in it, which detects all these sort of things. So they have a gyroscope. A gyroscope is something which has a rapidly spinning inner wheel, will maintain its direction in space even if the outside framework changes. So with that, it can actually understand the angle which is staying in the space, and it can calculate the values. And how does it understand at what point of space it is? It has got a sonar, ultrasonic sensor, which constantly sends ultrasonic waves below. You all know this is like 8th grade physics. How the sonar works. You constantly send waves. The reflection is calculated, and that is used to estimate at what altitude the drones are. So that is how that's how it figures out at what point of space it is. So, this Parrot AR drones has got it can measure up to 6 meters high 6 meters high, and if it goes above 6 meters, it's got a pressure sensor as well, which detects the pressure and estimates the altitude. So all the sensors, and then there are a lot more sensors, which I'm not going to talk about, which won't be relevant to the talk right now. But then there are a lot more. All of them act together. All of the sensors extract the values, sends to the control algorithms, and this control algorithm, what makes them float in the air. So if I want, it will stay there. It will stay there forever. We can have it here while the talk is going on. So these control algorithms takes input from these drones, sends it back to the motor, telling that this is what you have to do at this point of time to stay floating. Understanding these control systems is very, very awesome. You can understand the learned navigation technology. You can learn the drone navigation technologies embedded into it. Learn the autonomous decision-making unit. So this is actually an autonomous, function. It's going to do on its own. What is happening? So, hello. Okay, I think it's working here. Understanding how these flying robots work is one of the things which we are going to do. How do we do it? For me, to understand how this control algorithm works, the option I had was to reverse engineer the firmware. I'll tell you about Parrot, the black one. Parrot has a real-time operating system, which is an embedded Linux running an ARM processor. It manages the Wi-Fi, video sampling, image processing. Everything is done in that firmware. Then they have a specific program called program.elf, a Linux binary, which manages the entire drone. So all the actions which you saw right now are managed by this small program. It's like a 2 MB file or something. AR Drone has not made this program open source, but a lot of people have tried to reverse engineer this program and create a custom program.elf. So that was one of the confusions people had. So the only way to understand the control is via reversing the application itself. So when I say why we have to do reverse engineering, you would be asking why not do a dynamic analysis? Well, you can install a GDB on this drone. I mean, you can compile one, install one, but the problem is when you set a breakpoint, the motors would not get any signals, right? It'll actually crash. It would not stay floated, or you would not be able to do a dynamic analysis like the way you do with other applications. Now you might ask, why not you take the binary, which controls the drone, and run it on a different machine, a different ARM Linux machine? Well, the problem is the sensors which it needs to take data from are not there anymore on the dummy machine. So you cannot, it's very hard to do, I mean, actually it was not possible to do a dynamic analysis at all. If anyone has any ideas, I'm open to listen to it. So reversing the auto landing feature. So for the purpose of demonstration, we will take one small feature, which is the auto landing. I think I'll just demo that feature again. The auto landing is kind of interesting. Now this thing is in the space. I'm going to click a button which tells the drone to automatically land. So it should normally come back to the same place, but I did not do anything. It actually calculated where it should land, and when it came to the right place, it killed its motor, right? I was not, that's actually an autonomous action. So we choose, there are multiple of these sort of things in this device. We specifically choose understanding how the landing feature works, how it actually calculates things. We just saw the demo, how it actually lands. So we started with okay, one of the biggest challenges you have when you deal with a drone is how to extract the firmware, or how to extract the binary which controls these drones, right? Well, one way is you have firmware updates for many of the drones. You can see if you can trigger a firmware download, and then you can have a copy of it. In the case of Parrot, they had a firmware download, but the problem is the firmware was a custom package. I couldn't fully extract the binaries out of the firmware. But there was another feature that, this has got a telnet server running on it. Once the machine is up, you can telnet into it and grab a copy of the binary. I did that, and I started reversing. So one of the interesting, so I obviously use IDA. IDA Pro or IDA could be used. Hooper or whatever of your choice could be used for this particular thing. So this goes for reversing any application. There is something called as data sections, which has got string references, strings, which are actually hard-coded in the application. You can first start with looking at them. When I looked at that, there was a particular string which was actually used in a debug function. So if you see at this particular code, on the right, you see the function name, which is being referenced multiple places. This function is like a print debug info function, which is being called from every other function. And this has got information about what each function does. So I use this particular thing if you look at the assembly code, you can see a BL instruction in the middle and VS printf. BL is like the call instruction for ARM, which is actually, again, printing the value. So this function was helpful for me to figure out, because Parrot people have actually put takeoff code or landing code and all those sort of things. With that, I was able to figure out where the functions and where I have to look for. And once I was done with that, I figured out something that, the .data section, again, the raw data section, had references to serial ports. So what happens is, for the drone to communicate to the hardware, like the motors or the sensors, they expose a serial port which you can read and write values to. And these serial ports are yeah, okay. So these serial ports are exposed. The sensors are exposed by serial ports. So in the data section itself, the serial ports were visible. I was able to find from the comments, I was able to find what serial port reference to what. Like you can see TTY0 is for rotors. If you control that serial port, you can control the motors. You can control data, get the value from gyrometer from the PA2. Like that it goes. Another thing I did is I ran the program on strace, which gives me all the system calls which the drone library makes, which gave me some idea about all the input-output controls, which the drone is going to make again with the kernel. So our specific aim is to look at the auto landing feature, the code that makes a decision for the auto landing. So each activity of the control program runs as a separate thread. The stabilization control is a loop which takes altitude and velocity input from the sensors. So if you see over here, there are multiple threads started by the program. Each thread would be doing a job, a specific job. One of the threads was responsible for doing the stabilization as well as the landing. So this was the code which we had to look at. I'm not going in deep about the reversing part, but from the code, so this was the approach we took. From the approach, we were able to generalize the algorithm which they used to calculate where it should land. So can you see the code? So the code goes like this. It takes, uses the gyroscope, ultrasound sensors, then the bottom camera. There's a bottom camera as well, and the front camera to calculate an altitude estimation as well as a velocity estimation. It takes that value, sends it to that small program. It's a pseudo code which is very similar to what it had actually, and and the altitude and angle is calculated using a formula. So so we found a small bug. It's a funny bug. Can you spot what could go wrong in the small program? I mean, if you were to hack this, what would be the thing you would be trying out? So I'll explain the program. It's got a counter sort of thing. The counter has the current altitude. So if it's a 6 meter high, it's 6 meter. Then it's a while loop which checks whether the counter has reached 2 centimeter or something. That's like it's closer to the ground. If not, it'll continue to hover down, keep hovering down. And then again, the altitude takes data from the sensor, and the loop continues. Okay, I'm going to tell you what happens. What happens is, it takes input from the sensor directly, and it does not check if the current altitude is relative to the previous altitude. That means, if you can fake the sensor, making it believe that it's at 3 feet, it will believe that. It would not check if it was at 6 meter high. It would not check whether it has crossed 5 meters or 6 meters. If you can tell the sensor that it is 3 meter, it would believe. It doesn't check for the values which was before. It directly accepts the value which is, what is right now. So it's a small logical flow. And what happens is, what you can do with this particular law? All you have to do is fake the sensors. You can use something like this, a small drone like this. All this drone has to do is go near the sensor. The sonar would try to locate the space. I mean, when it's trying to land, you send the small copter, stay somewhere near the sensor. The sensor now thinks that it has already reached 0.5 mm, and it will shut down the motors. I'll show you that I don't have a small, what do you call it? I don't have a small copter, so I'll just show this using my. So I'm going to do the auto landing, and what happens is, so the same thing you can do with that microcontroller. All it has to do is, close the sensors for 2 seconds in the space, and it'll actually shut it down. This is actually a funny hack which just demonstrates how this control algorithms work. That means, there would be so much logic flows in it because it takes input from the sensors around. It's the same principle, the data validation which you did in all your web application. If you just don't validate an input, even if it comes from a sensor which is around, we can actually create problems. This, of course, is a toy, but I'm pretty sure this sort of implementation bugs would be there in other drones as well. So this is funny, but when I was doing all the research and all those sort of things, I used to do it in a tennis court behind my house. And what I understood was there is an awesome hacker whom I didn't knew who lives in my apartment. So when I was doing all this demonstration, he comes in and gives a quick demo of how you can hijack any drones anywhere in the world. So this guy comes, teaches me how you can hijack any quadcopter anywhere in the world. So in few seconds, the quadcopter would fly, and all of a sudden this guy comes and then finds a way to kill it down. So just wait for it, and the quadcopter will go high, and the hacker would come and. This actually happened. You really don't have to do all the reversing. You just have to throw something. I was like, so the point is these devices would be low or flying in a low altitude, and pretty much you can shoot it down. Wouldn't be hard. I don't know how Amazon is going to come up with a solution for this, but then I thought I would include this in the presentation, just So the concept of Maldrone. So what happens if? So we understood the control theories used, how we can reverse them. What if we can actually backdoor something? What if we can backdoor a device, something like this? Or what if a device which you already brought? What if this parrot is already backdoored? Or maybe a better version of this is already backdoored? How do we know that? Because the DJI is from China. I'm not saying anything, but I'm just saying. So, but it's expensive. So a lot of people ask me this question when I publish the blog: is Maldrone the first malware for drones? Especially the people who didn't read the blog were asking this question. What happens is AR drone, that particular thing, exposes a high-level API. This is open sourced. This API lets you control the drone at commands using UDP. So if you see me controlling the drone from my computer, it was using an API which was made available by Parrot Drone for programming purposes, and I used those to communicate to this particular thing. A lot of previous research for backdooring drones used this specific API, and that was specifically for Parrot. It would not work on anything else. So my idea was to document all the generic ways you can backdoor a drone. And I wanted the backdoor to work on all drones, irrespective of the model. So both DJI and Parrot both works on ARM Linux, so it should work on both. So that was the idea I had. So yeah, and then there was something called Skyjack, people who ask. So Sami Kumar, another researcher from US, he demonstrated a way which you can hijack Parrot drones. So what he did is the Parrot by default doesn't have runs on Wi-Fi, and it does not have a Wi-Fi protection. So if I'm connected to the as a commander, I'm connected to it, no one else can connect to it. So what happens is you can actually do a DOS attack, disconnect myself, and you can connect to it. All right, same functionality, just disconnect me and you will be able to take over. So that was his attack. So that was an exploit for Parrot drone. Maldrone is actually a malware for drones. There's a huge difference. This was very specifically mentioned on my blog, but what happens is people have the tendency to read articles. Even one guy wrote an article that they should call me to stop White House from not crashing drones. So stories were there, and they even mentioned the blog article, but then many people failed to read those. So these sort of questions were there, and so I just wanted to mention that. So the requirement for Maldrone I had were, so how much time? 35 minutes. 35, right? I have 10 more. Okay. So the requirement for when building Maldrone was it should work on multiple drones running Linux-based. So Parrot drone is a toy. This thing is also a toy, but the POC should not be specific to Parrot. It should be very generic. Because what we are trying to do is we are trying to document ways how you could backdoor a drone. So that in future someone wants to analyze a malware for drone, he should be able to look at the documentation and figure out what. So it's all about idea sharing and thinking. So a couple of ideas I had were to create a custom firmware or create an alternate for that. I told you about the program.elf file which controls. Create an alternate for that program and then backdoor it, or hook into program.elf itself and do task. So I'll explain why. So writing a custom firmware, the problem is each devices would have a different firmware and a different structure. So you cannot make a firmware for Parrot and then you cannot ship it to Phantom. It's not possible. But a lot of guys have created firmwares just for Parrot drone, custom firmwares, not stable, but people are trying to do it. And there are a couple of references for that. So that's the reason why I didn't go in that path. Hooking into program.elf was another way of doing it, but the problem, I'll tell you how you can hook into it. So, like I said, the Parrot drone has exposed a couple of serial ports to communicate to the sensors. Program.elf uses Linux syscall open to open these device drivers. So if you see the pseudo code on the top, that's how it opens a serial port. It reads the serial port using the Linux syscall open and talks to it. So if you want to hook into this particular program, you can use a functionality of Linux called LD preload. We can make the Linux system load any library by specifying this particular variable, environment variable. So what happens is hook.so is a shared library which has got this particular code. When you start program.elf, this particular code, when it makes a call to open, the code which is mentioned in this particular hook.so would get loaded. That means it would not go to the actual syscall open, it will come here. And what we have done in the hook.so is, we have our malware code here, if you want, and then it will actually point to the actual file of the open syscall. So people have went through this path as well. So they have used it to tap video signals, video feeds from the drones, and they use this particular thing. But the problem is this would also become very specific to drones, because you need to know what all syscalls to tap, where all you have to inject, and all those sort of things you need to know. It would become, again, very proprietary to Parrot drone, which we did not want. So our idea about Maldrone was it should work on both Phantom AR drone or anything which belongs on AR Linux. Both drones exposes a Linux serial port to communicate to its sensors. So the idea was, but then the problem is if a a serial port programming uses Linux is called open to read devices, that particular serial port would be locked. Another program would not be able to read or write to that particular thing. So why not make malware which act as a proxy, which would stay between the serial ports, your sensor, malware will stay in between, and the controlling application. And Maldrone will actually talk to the serial ports, and it communicate back. So the procedure code for Maldrone was to actually set up a serial port proxy first. It then kills the actual commanding program, set up a serial proxy for navboard and others, and find all the serial port references in the binary, patch them, make it point to your own serial port. Now, all the redirected traffic would go to your, all the redirected traffic would go to go via Maldrone, and Maldrone would act as a proxy. This would work on both these drones because the basic architecture remains the same. All you have to do is find the references and patch them. So this is how it by default works. You have the drone controller code, program.elf, Maldrone, which acts as a fake serial port, and then you have the hardware device, which Maldrone talks to. He stays in between. So I programmed this in Go language. According to Go's definition, Go is an express concurrent garbage collected programming language developed by Google. The reason why I choose Go was it has got an amazing cross compilation. You can program in ARM, and then you can port to Linux ARM, and then you can port to Mac OS pretty easily. It's like hassle-free. And it's a very good alternative for OS programming as well. Moreover, I wanted to learn this particular language, so I thought I would stick to this. And then there was this guy who has developed something called AR drone, Go drone, which is again alternate for program.elf, which is written in Go. That was acting as some reference. So I choose Go language, and then I created a Python program which would upload the malware to the drone. So Go programming language is used to create Maldrone, and a Python program which will upload Maldrone to the drone. So this is how it look after patching. So once Maldrone is installed, the malware installed on a drone, it actually finds references to serial ports. So on the first, so how it looks before patching, you can see. I don't think you can see. Yeah, so you can see it's TTY0. That's the actual reference to the serial port. But after patching, what happens is it would point to whatever I want, and then it will start opening. So this is a trace of the function. And the payload was simple. It should reverse connect. It should reverse connect to the attacker once the malware is installed. It should kill the actual controlling program. Then it should set up the fake ports, serial ports. Then patch the binary. And every time the drone starts, your malware should come up. So 42 minutes. So I'll have a demo. If the demo doesn't work, I'll show you a video. So that's how we control the program. So I think so what is going to happen right now is the drone is going to fly. We'll infect the drone with the malware. The malware, after a particular point of time, it will install the program, and for patching purpose, it will shut down the program.elf. That means it's going to fall down like a brick because it has lost control of the motors, and that's going to happen right now. So take off. No. Oh shit, sucks. Sucks. I think I screwed up. So, okay, so we'll stick to the second plan. Yeah, so it doesn't work when you need it. It would never work when you need it. Fine, you'll stick to the plan D. You got from the and then I'll try this out. How much more time do I have? So now it uses the APIs to communicate. Now next thing, it flies up and we'll try to. So now we'll start the drone in autopilot mode and we'll try to infect it. Can give me like few more minutes, we can try with demo again. Or maybe later, okay. That's fine. So now the program actually, so we're going to send the payload. If the package is uploaded, it takes 2 seconds, wait. Now it does a reverse connection back to our computer. It does a uname A. It shows you a Linux computer which is running. So this is going to shut down in like 3 seconds. If these guys are going to give me more time. So yeah, so thank you. We can actually do a demo outside. We'll try it out again. I need to figure out what happened. But these are the people I need to thank. Garage for Hackers for being awesome. The Static Security team for being awesome again. Team nullcon. Mrityunjay, the security manager, is here. So if you're looking for a job, he's a guy, and we have a booth over there. Rashid Bhat for all the reverse engineering help. Yashin Mehboob for bringing the drone all the way from Dubai. This one guy I didn't mention because I didn't ask him. Tobias for bringing it from Germany, and Mohit Kumar for all the great support, and my fiance for not annoying me throughout the work. So thank you, and I'll try for the demo if 1 minute. Oh, thank you.